so in the last lecture. So we developed our first quadratic element last week. This is basically a quadratic element because it has 3 nodes. Oops. And then this element will interpolate using a polynomial, second order polynomial, to try and integrate or try to find the displacement. We developed the shape functions for these elements. I'm just going to write them down. So n1, I'll just take the full space. n1 is equal to 1 minus 3x over L plus 2x squared over L squared. n2 is equal to 4x over L minus 4x squared over L squared. And finally, we have n3 is equal to minus 3, oh sorry, it's minus x over L plus 2x squared over L squared. We did the shape functions first, and then we did the B matrix. So the B matrix was, this is just the derivative of the shape function, so it is minus 3 over L 4x over L squared, and then we have 4 over L minus 8x over L squared, and finally we have minus 1 over L plus 4x over L squared. So this is the B matrix. We know the strain is basically the B matrix multiplied by the displacement vector. We know obviously the stress is just the elasticity modulus multiplied by the strain. And then based on these, we developed the stiffness matrix. I'm just going to also write the stiffness matrix here. So the stiffness matrix is EA over 3L is 7 minus 8, 1, this plus 1. Then minus 8, 16, minus 8, and then we have 1, minus 8, and 7. So this is the stiffness matrix. We use the stiffness matrix, or we use this element to solve one problem. So this is example number 8, I think, and we solved this. We got these displacements. I'm going to discuss them in a minute. But what we are going to discuss mainly this week is going to be limitations for this type of element. So what sort of problems we can solve with, what sort of problems we cannot solve with. Continue, I mean, just if you remember when we did the shape functions for the linear element, we did draw the element. So I'll probably just draw the element as well. Not the element, probably I just draw the shape functions for this element. I'll try to fit them in here. Okay, so if you want to draw the first shape function for this line element, I'll draw them underneath the element. I think this would be better. So this is the element. If you want to draw the first shape function, so this is x and this is n1, then in this case, this is going to look like this. See, for the first node, you have the value. I mean, this is the shape function associated to the first node. So at the first node, the value of the shape function is going to be equal to 1. Then at the second node and at the last node, so I assume that this is the x at the last node, you have the value to be 0 and 0. So this is a parabola. So the parabola is going then to look like this. And then here is not perfect drawing, but assume that it is basically passing. Yeah, I probably just shifted slightly here. Yeah. So it is passing through 0 at the second node and passing through 0 at the third node. And at the first node, it is equal to 1. The same thing is true for the second shape function. So the second shape function is associated, just use this pen here. So this is x, this is n2, and then n2 is going to be 0 at the first node, and then it gets to 1, so somewhere here, and then it goes back to 0. So if you look into the second shape function, the second shape function would look like this. So it goes from 0 to 1 to 0. It is 1 at the second node, because it is the shape function associated to the second node. And if you look into the last shape function, so this is x and this is n3. So the n3 would be similar to n1, but in a reverse direction. So this is again 0 here and 0 here and 1 here. So it would look like this. Oops. So it is 1 here and 0 everywhere else. Just use the dashed line here. Now you can multiply just like what we said for the first element, for the linear elements. You can multiply. Oops, this is too thick. This is the one. So you can multiply the first shape function with n1, so with u1, the second shape function with u2, and the last shape function with u3, and combined you can produce any displacement field. So it is u1 n1 plus u2 n2 plus u3 n3, and you can recover pretty much any parabola you can think of. I mean, any parabola you want, you can recover it using these three parabolas. So if it is this one, or if it is probably this one, or any other parabola, I mean, really any parabola you can think of, you can recover it using these three shape functions. Now, if it is a line, this can, I mean, a parabola is a second order polynomial, and a parabola basically can recover a line as well. So if you look into the first equation, we started from the parabola equation. It was ax squared plus bx plus c. And assuming that a goes to 0, then you have the line equation left, and you can represent any line. So you can basically represent anything that is second order or lower, and you can represent it exactly. So this is what you can do with the quadratic elements. Now, a parabola is a second order shape, or it's a second order function, so you can recover it exactly. And this is why you basically use these quadratic functions. And you, of course, you can also use them to recover a line. Now, one property I want to mention, I mean, it's not very important for you at this stage, but I just want to mention that these n1, n2, and n3, we call them basis functions, and they are basis functions because you can use them to construct any second order function. Exactly. So you basically can use n1, n2, and n3 as bases, and you construct any second order polynomial using them. And they have one property. So in order, I mean, think about it just like a normalization process. If you add them up at any cross section, you'll see that the value of the addition is going to be equal to 1. So look at the first node here, and the value of the first shape function is 1. This would correspond to 0, and this will correspond to 0. Add everything, the result is going to be 1. Take any section you want and add up things, you'll see that the value is always going to be 1. So look into the second node, this is 0, 1, and then this is 0. And repeat this for any cross section you want. You'll see that always n1 at this cross section plus n2 plus n3 is equal to 1. This is what we call the partition of unity property. This is basically the unity has been partitioned into these three segments, and this is correct for any shape functions for any type of elements. So it's basically we partition the unity into a number of basis functions, and then these basis functions, we use them to reconstruct any other function we are trying to approximate. And in this case, if the displacement field is going to be a quadratic function, then you can recover this quadratic function exactly using these three basis functions. I said that this is very useful for quadratic displacement fields, parabolic displacement, or if the displacement field would look like a parabola. And this would be the case if we do a distributed load. A uniformly distributed load would lead into this type of curved displacement field, the second order polynomial displacement field. Now, if it is the case, then when we solve this type of problem, we should be getting the exact displacement field. Now, I'm going to discuss the results we had in the past and the results we did when we solved this example. Now, if you remember this, what we did last week, we solved this. Here, I'll go back here. We solved this problem here. Probably, yeah. So we solved this problem here. And this problem we have been solving a few times already. We solved it once using one noded element, one two-noded element, and then we solved it again using two noded elements, and then we solved it a third time using this quadratic element. So this is the solution we have with the quadratic element, and these are the answers we have for the displacement with the quadratic element. So this is, you probably remember from last week. Okay, now I'm going to compare the answers we have, and you tell me which one is the correct one. Now, this is the solution we have using one two-noded element, and obviously if you use the shape functions and you cut at this section and you want to find the displacement at this section, the displacement here is going to be WL squared over 4EA. Now, this is the displacement at the midpoint, and this is the displacement at the end point. I'll probably just shift this slightly just to put it toward the end. Oops. Yeah, it's not moving. For some reason, it is not. All right, okay. I'll just put this one here. Oops. Oops. All right, so I'll probably just write it here. I think this is easier. Oops. Here. It's WL squared over 4EA. Okay, so this is the displacement at the midpoint, and this is the displacement at the end point if we use the one two-noded element. If we use two two-noded elements, then the displacement we have at the mid node is 3/8, and the displacement we have at the end point is 1/2. And now we use this one three-noded element, the displacement we have are 11/32 and 1/2. Now, if you compare the displacements at the nodes, if you look at the very last node here, you'll see that this is the same like this one, the same like this one. What these cases are failing to agree on is just the displacement at the midpoint. This is giving us one number, this is a second number, and this is a third number. Now, in order to identify which is the correct one, we did the solution. We did an analytical solution for this problem, and we found that this is the case where we have the accurate number. So this is the exact solution. Now, why you are not getting the exact solution in this quadratic element? Do you have any suggestions or any ideas? why we're getting the exact solution for this case, we said that always for the finite element methods, always at the nodes, we get the exact solution. I mean, even if it is a poor approximation, in general, you should be getting something exact at the nodes until you're really producing quite a lot of, I mean, you're introducing some mistakes into the assumptions you're making. At the nodes, you should be getting the correct solution. Now, this is the case at this node, and this is the case at this node, and this is the end node also for the first element, or the end node, or the first node at the second element. So we are also getting the exact solution at this node. Now, in this case, we are not getting the exact solution at the midpoint because of the assumptions we made when we lumped the mass. So when we lumped the force. So basically what we solved, if you remember, what we solved, it was not the exact problem here. It was some similar problem where instead of a distributed load, we have a concentrated force. I'll probably just use red for that. We had a concentrated force. So this distributed force was replaced with three forces. The first one was WL over 4. The second was WL over 2. And the last was WL over 4. Now, if you add WL over 4 plus WL over 2 plus WL over 4, you'll see that this is WL, which is the full amount of the force. So this is an equivalent load vector that will basically apply the same amount of force on this cantilever, but it will not give you the exact representation of the way the force actually is acting in the real world. In order to have that, we also need to partition the force in a way equal to the shape function. So just like I said, we are partitioning this displacement into these three basis functions, these three shape functions. We need to partition the force exactly in the same way. And by partitioning, I mean the first part of the load. So the full load is WL. This is the full amount. We need to distribute this into three pieces. And one piece would correspond to each shape function. Now, as I said, if you add up these four, or if you add these shape functions together, they will produce a unity. So basically, if you add them together, they will produce a square that would be of a unity size. So this is 1, 1, and this is between 0 and L. So add them together, you will produce a unity, you will produce a rectangle. Think about this load to be this rectangle here, and you want to partition it exactly by the same amount that each shape function would contribute into this rectangle. And the way to do that, you need to integrate the load with respect to the shape functions. So basically, you need to probably just to draw the problem here first. This is the cantilever, and this is the distributed force W. So what you need to do is you integrate the shape function between 0 and L and multiply it with W. You do this for N1, and you have the value of the first, the value of the load that should be allocated to the first node. You do the same thing for the second node, not using the second shape function. And you do the same thing for the last node to get the loads at the third node. All right, so I'm going to do this just for one case for the first shape function. So I'll just take the shape function from here. And just hide this guy here. All right, so the value for the first node should be the integral between 0 and 1. I'm going to paste the shape function here. And remove this n. So this is the shape function. And the shape function is multiplied with W and integrated over X. So if you integrate that, you will get X. This is minus 3x squared over 2L. And this is plus 2x cubed over 3L squared, running between 0 and L. So this should be L, sorry, because you are integrating over the length. And this is W. So this is just W multiplied from left or from right. It wouldn't make any difference. So W1 then is going to be W multiplied by, if you replace this X with 0, this is going to go to 0. Anyways, it's not going to add any values in there. So I'm just going to replace the X with L. So it is L minus 3L squared over 2L plus 2 over 3L cubed over L squared. The cube will go away with the L squared, the square will go away with the L, and we will be left with L minus 3 over 2 L plus 2 over 3 L. So this is basically 6 over 6, and this would be then 9 over 6. And this will be 4 over 6. So 4 over 6 minus 9 over 6, this is minus 5 over 6. 6 minus 5 is going to be WL over 6. So the value of the load you have at the first node is just W over 6, WL over 6. And if you repeat the same thing for the second shape function, you'll get for the second shape function, you'll get W2 is equal to 4WL over 6. And if you do the same thing for the last shape function, it is going to be WL over 6. Now, if you add them together, so if you add W1 to W2 to W3, this should be equal to WL, which is the case. If you add them up together, they will add up to WL. So it's basically redistribute, reallocate the load to the nodes according to the shape function. So the loads would take, each node will take a load that is equivalent to the amount of area that is associated with the shape functions it has. All right. Now this is correct if the load is uniformly distributed, but it is also correct if the load is distributed in any other way. So basically, if the load, this is a uniformly distributed load, but if you have something that is non-uniformly distributed, so for example, you have a very large amount, so this is 4W, and then is linearly decreasing. I don't know probably how to represent this as a triangle. And this is linearly decreasing up to 0 here. So it is starting at 4 and reducing to 0, for example. If you have that, you can also use this concept of the allocation according to the shape functions. And this is also correct for any type of load. So any type, any kind of distributed loads can be allocated exactly in the same way, just like what we did for the uniformly distributed load. To solve the problem again, this time I want you to use the equivalent load vector. So this is again the same problem we have solved in the last lecture, and we used an equivalent load vector. Now we are going to change the equivalent load vector. So instead of WL over 4 and WL over 2 and WL over 4, we have 4 WL over 6 and WL over 6, and we have F1. Obviously, F1 is whatever reaction you have in there added to WL over 6. So you can use this equation in order to be able to find the reaction. Okay, so I want you to solve the problem again, and in this case you are going to get the exact answer we have from the exact solution and also from the two noded elements, and I want you to make sure that you can get these answers. So I will give you 5 to 10 minutes to solve this problem, please. Once we have the displacement, just like we did in the past, just once we have the displacement, we can use them to find this strain. I'm just going to write the strain expression. I'm going to write the strain expression here so that you can see it. So the strain is basically the B matrix multiplied by the displacement vector. And the B matrix is, I just take it from here. Yeah, it's nasty. Oops. Okay, so this is the B matrix. I'll just take it here. I just delete these parts here. And then move these ones to the top. Okay, so this is the B matrix. We multiply it with the displacement vector. Just going to write the displacement vector we have in this case. So the displacement vector is just what we have here. So this is basically the displacement vector. This is 0 and then 3 over 8. So it is 0, 3 over 8, and then we have 1 over 2. And obviously the whole thing is multiplied with WL squared over E A. So if you expand this, U is going to be, sorry, this is the strain. So the strain is going to be this thing here multiplied with 0, and this thing here is multiplied by 3 over 8, and this one here is multiplied by 1 over 2. So I'm just going to write these two parts as the first one is just 0. So it is 3 over 8, 4 over L minus 8x over L squared plus minus 1. I'll probably just strike the half first. Minus 1 over L plus 4x over L squared. And this whole thing is multiplied by WL squared over E. So if you look into this expression for the strain, you'll see that this is a function of x, and you have only x in there. X is the variable. So if you want to plot that, if you want to draw the line, yeah. So if you want to draw the strain, This is x, and this is the strain. So if you want to draw that, you just substitute x by the value of L. So for example, if you want to start by x equal to 0, and then you will have the value of the strain at this point, x equal to 0, and then you substitute x with L, you will have the value of the strain at this point. So you check them, you'll find the value for the strain. The value for the strain at 2 points is enough to draw the strain, because you know that the strain is going to be a line. So you draw the line, and you know that this is how the strain would look like. Now, this is compared to before. If you remember, before we had the strain is minus 1 over L, 1 over L, multiplied by U1 and U2. And if you expand that, you'll see that excuse me, I'm using my laptop at home, and my laptop and the tablet I write on is not quite convenient. Okay, so it is minus 1 over L multiplied with U1 plus 1 over L multiplied with U2. And if you look into this equation, this is an equation for a constant. It's not an equation for a line. This is basically just one constant, and the stress would look like this. Just like a constant. All right, whereas this one can be a line, and the line can be anything. So it can just vary in any way you can think of. All right, so this is basically the key advantage of using the, this is the key advantage of using the using these quadratic elements. So basically the strain can also vary, not constant like we had in the two noded elements. All right. So basically one limitation we had, and now we have overcome, is the equivalent load vectors, basically how the load need to be allocated. So this is not straightforward as it was in the previous case. Now we are going to discuss a second limitation for this type of problems, or for this type of elements. To know the limitation, I want you to solve this example. So I want you to solve this example and do the full solution, and also do the strains. So solve the example, get the displacement. These are the values you should be getting for the displacement, and this is the value you should be getting for the reaction. And then I want you to go one step further and evaluate the strain. Obviously, the strain is the B matrix multiplied by the U matrix. So once you have U, you already have the B matrix, and you multiply them together. I want you to get the strain. And once you have the strain, the expression for the strain, and you have the displacement, and I want you to take a look into this solution you have and tell me if you can distinguish any difficulty or any problems or any limitation to this type of elements. I mean, there is a limitation in this type of elements, and you should be able to see it if you see the solution for this type of example. And if you don't see it, then we are going to discuss it further in the second example. All right. To be able to see that, I want you to solve this full problem, get the answers, make sure you can get the correct answers, and then I want you to find an expression for the strain, and then take a look into this. I'm going to give you 15 minutes to solve this, because this is quite important for you to see. All right. You can see that the answers are correct, and now I want to continue and do the strain, just like I said. This is the expression for the strain here. The B matrix multiplied with the displacement vector. If you can carry on, draw the strain and see if you can see anything unusual or And this is the expression we have for the strain. Just have a look into this. I mean, if you have been able to get the expression yourself, please confirm that you got the correct one. If not, then have a look into the solution we have here and tell me if there is something not quite usual in there or something that is not quite correct in there. I mean, I'm talking about a fundamental issue related to the element itself. I mean, the solution, mathematically speaking, you have done all the correct mathematical steps and you are getting what you should be getting mathematically. But I want you to think about this expression. Would it actually reflect the reality or not? We do exactly the same thing. I want to solve this example now. See, this is a cantilever. The cantilever is fixed at one end and is loaded at mid-length with W. This is exactly at L/2. I did the problem, I solved this problem using the two-noded elements. So I needed two two-noded elements. This is element number 1 and this is element number 2. I did the full solution of this problem. You can see here the stiffness matrix. You can see the displacement vector. You carry on solve this, you get this displacement at the second node and this displacement at the third node. This is what you get from solving this problem. Now I want you to continue solving this problem, but then using this one three-noded element. So I want you to solve this problem again using one three-noded element and get me the solutions. All right, so this is the solutions with one three-noded element. Make sure that you can get the correct answer, and we are going to discuss this. I want you to have a look into the answers we have here and the answers we have here, and I want you to think about them, and we are going to discuss the example further. All right, so make sure you can get the correct answers first, and then we are going to discuss this a bit further. Just summarize everything on one note. I just start a new page here. Okay, so we have this example, cantilever fixed at one end, right at the mid-length, we have a load W, and this is exactly at L/2. The full length is L, and we have E and A as the material properties and the geometry. We solve this using two two-noded elements. We have delta 2 to be, I just copy the answer, WL/2EA, WL/2EA, and then delta 3 is WL/2EA. Now, if you look into that, this is two noded, and then we have one three noded. We have delta 2 is equal to, just going to copy the answers from here, 7 over 16, 7 over 16 WL over E, A, and then delta 3 is equal to WL over 2 E, A. Right, see, the first observation, delta 3 is the same in both cases, WL over 2EA, WL over 2EA, this is correct. If you look into the second node, you will see oddly, or probably for a good reason, that this value here is exactly the same like this value here. Since both displacements are exactly the same. Two-noded element is able to capture this behavior, whereas if you look into the three-noded element, the three-noded element is failing to capture this behavior. So it's taking the displacement to be at the end as the maximum displacement, and then is reducing that slightly as you are moving toward the center. Now I'm going to explain this in terms of the stresses, and probably once you see the stresses, you will see what is wrong with the three-noded elements. So probably just use a fresh page for that. I'll just carry on here. Now I'm going to draw the stress from the two-noded elements and draw the stress from the three-noded elements, and then eventually I'm going to draw the exact stress. Let us look into the exact stress first. Probably this is better to start from the exact stress. So you have the cantilever fixed at this point, and think about the stress starting from this free end, and you are moving inward, right? You are moving inward. This part is no stress in there at all. This part is still free from stress. This part is still, as you are moving in this direction, the stress is free in this part of these elements up to this point, right at the middle. Starting at the midpoint, you have a force active on your cross section A, and this is going to be your stress. So the force is W. From this point onward, the force is going to be W divided by the cross section, and is going to be constant for the rest of this length. So it is going to be some constant stress. So if you look into the stress would look like this. So constant value for the stress up to the mid length, and then it is 0 for the rest of it. So just 0 stress in there. And this one is W over A. W over A. So this is the amount of stress you have in there. Now, stress is going to be the same like the strain if you just divide by the elasticity modulus. So I'm just going to write E here and E here. All right, so this is the amount of the strain you have. Okay, now let us look into the solution you get from the two-noded element. So the strain you have from the two-noded element is minus 1 over L multiplied by the displacement. I'm thinking about the first element now. So the first element is 0 WL over 2EA, right? So this is the stress, or this is the strain you have. So I'm just going to multiply it. So the strain in the first element is just going to be then WL is just this part here, is WL over 2EA multiplied by 1 over L. The L is going to go away with the L, so you'll be left with W over 2EA. Right, so this is the strain you have in the first element. How about the second element? In the second element, again, you have minus 1 over L, 1 over L. You have WL over 2, so this is the displacement you have at the second node. This is here. And WL 2EA, sorry. And you also have WL over 2, over 2. Yeah, I need to move slightly lower. Over 2EA. And multiply minus 1 over L with WL over 2EA. WL over 2EA multiplying with, sorry, so it should be 2. yeah, you need to replace it eventually, and it's going to be too late. Yeah. And then this is plus and minus is going to cancel each other, so it's going to be 0 anyway. All right? I'll probably just write that minus 2 over L WL over 2 EA, and 2 plus 2 WL over 2 E is 2 EA. So this is going to cancel with this, and then you'll have 0 as a result of that. All right? So this has produced a constant amount of the stress and then a 0 amount of the stress for the second part. Now I'm going to do the same thing for the 3-noded element. I'm just going to do the strain is going to be the B matrix multiplied by U. Again, just the same expression. I had the B matrix somewhere here. I just copy it from there. I'll probably just copy it from the first slide, is easier. And we remove this part here. And you see that this is epsilon is multiplied by the displacement. And the displacement we have in this case, I'm just going to go back here, is 0, 7 over 16. And then 1 over 2. Obviously, you have EA. Sorry, it is WL over EA here. So expand that. I'm just going to expand it. So epsilon is 0 multiplied by this is 0. So I'm just going to start from the second one. 4 over L minus 8x over L squared multiplied by 7 over 16. And then the second part is minus 1 over L plus 4x over L squared multiplied by half, and the whole thing is multiplied by WL over EA. Now, I want to draw the stress or the strain resulting from this case. So I have the cantilever here. This is the full length of my cantilever. X is equal to 0 at the beginning, and X is equal to L at this free end. So at this point, I just substitute X with 0. So epsilon is going to be here. This is 0 is going to cancel the entire thing, and this is going to go to 0 is going to cancel the entire thing. So I'm just going to write them as 4 over L. So it is 4 over L multiplied by 7 over 16 plus minus 1 over L multiplied by half, and this whole thing is multiplied by WL over EA. So 4 will go away with the 16 and will leave me with 4, and this can be rewritten as 2 over 4. So basically you have minus 2 plus 7 is going to be 5 over 4, and the L will go away with the L here, so it will leave me with W over EA. So this is at X equal to 0. Then at X equal to L, we will have, I'll just write it somewhere else. There's no space left for me here. Yeah. So this will then give us here. Will give us the value for epsilon to be, now I have 4 over L minus 8. This x will be replaced with L, so it's going to cancel the square and it's going to leave me with minus 8 over L. Obviously, this is multiplied by 7 over 16, added to minus 1 over L, 4x over L squared. X is replaced with L. The L will go away with the square, so it's going to leave me with minus 1 over L plus 4 over L multiplied by half. And then the whole thing is multiplied by WL over E. Okay. Now, we have 4 and minus 8. This is going to be minus 4. Minus 4 over L multiplied by 7 over 16. Just make it over 16. Now you have minus 1 plus 4. This is going to be plus 3 over 2L. And this is multiplied by WL over EA. So again, the 4 will go away with the 16. Just make it 4. And here I can make it 6 over 4. I have minus 7. See, this is a minus sign here. This is a minus sign. Minus 7 over 4 plus 6 over 4 is going to be minus 1 over 4. And the L, again, will go away with the L, and I will be left with W over EA. So if you look into the strain at x equal to L, you will have minus 1 over 4 W over EA. If you look at the strain at x equal to 0, you will see that this is 5 over 4 WEA. Now I'm going to draw that on this one here, so you can see how the strain would look like now. Just use a different color. It's not for this one. Okay, so you'll see that the strain at this point is 5 over 4 W over EA. And at this point, it goes to minus 1 over 4 W over EA. So it is moving from positive to negative and is crossing 0 at some point. Right, it's just an exaggeration. But this is how the strain would look like. Now, if you look into the presentation, I've done this in a much neater way, so we can see this here. So this is 5 over 4. 1.25 is just the same, and this is minus 1 over 4. This is 0.25. I mean, this is the stress, but if you divide it by E, you will get the strain. So I had the strain in there, but the stress is just the same thing. Now, the red color, the curve here you have, is the red one, is the stress we have from the 3-noded. And if you look into the rectangle is the stress you have from the analytical problem. It's just the analytical stress. All right, so this is the value for the analytical stress. Now, this is W over A. This is the cross section. Now, if you look into the finite element method, the finite element method is trying to fit this rectangle here using this line. Now the line is trying to match the rectangle to the best it can, but it is going to miss the amount miss the exact stress, miss the maximum stress by 25% extra at this end, and is going to miss, now this is extra, and by mid-length is going to miss 50% of the stress by underestimating it. And if you look into the tip here, you'll see that the stress at this tip here is 0.25 compared to actually it should be 0. So this is a lot different than 0, and it's going to give you some value for the stress that is not there. And this is also correct for the entire half, or the entire other half of this cantilever. Now this is happening because the finite element method is limited to the approximation you introduce into the method, right? See, the thing is, the finite element method is trying to have this line matching this step function. Is what happening. You have, this is x, and this is, for example, the stress. So you have a step function, the stress is constant, and then immediately is dropping to 0, and you are trying to fit this step using one line. Is no way that the finite element method is going to do better than what it did in here. So this is why it is limited. Now, how would you be able? And this is the limitation related to this quadratic element. So this is the quadratic element, and this is the limitation we have in there. Now, how would you be able to use this quadratic element, or are you able at all to use this quadratic element to solve this type of problems? I'm talking about this type of problem here. Can you use this quadratic element to solve this problem here? Can you do that? See, if you look into this case, instead of using, it's trying to fit a line to a step function. Now, instead of doing that, think about using two quadratic elements. So one element here and the other element is here. And then the first element will try and fit the quadratic function is trying to fit, or the line function is going to try and fit the first half. And this is basically constant if you consider it this way. And the other half is also constant, is 0, but is constant. And then on the interface, you have this discontinuity in the stress, which is the very existence of the finite. I mean, the discontinuity in the stress is the nature of the finite element method you are using. And this is called the Galerkian finite element method, and it is a basic feature of the Galerkian finite element method that you have discontinuity in the stress in between the elements. So the discontinuity is the nature of it, and then the line is going to fit the constant quite well, and the other line will fit the constant quite well. So if you repeat this problem, one more time, and instead of using one quadratic element, you use two quadratic elements, obviously it's going to be a larger system to solve, but you are going to get WL over 2EA, and it's going to be WL over 2EA for the second element as well. The two noded elements, so this is one two noded and second two noded. So this one noded element will only have the constant to fit into this constant, and a constant can fit fine in there, and a constant can fit fine in there. So this element would work just the same way like this one. Now tell me, which case do you prefer? Do you prefer two noded, or two three noded? to need a lot of fewer equations to solve if you are going to use, say, if you do the two noded elements, you are going to have 1, 2, and 3 equations. So you have 3 equations, 1, 2, and 3. Whereas if you look into 2, 3 noded, you have 1 and 2 elements. So you have 1, 2, 3, 4, and 5 equations to solve. So it's not going to be just that. On top of that, you are going to add the stiffness matrix also for the other element. So this is going to be plus 7 over 3. And then you have minus 8 over 3, 1 over 3. And just minus 8 over 3, 16 over 3, and 7. Or sorry, it's minus 8 over 3. And finally, you have 1 over 3, minus 8 over 3, and 7 over 3. See, you started from having only 3 equations, and obviously here you have zeros. So instead of doing this, and sorry for the not being so neat on my writing, but you started from 3 equations and now you have 5 equations. You see 1, 2, 3, 4, and 5. 5 equations. And instead of solving 3 equations, you are going to solve 5 equations, which is a lot more work for exactly the same reward. So you would not do that.